Welcome to the week 13 Math 2413 review. This is, I believe, the second to last week review we'll have, so there will be one more next week, and after that, that's it. So thank you for coming. And this one, we're mostly just going to get some practice with integrals, get a little more practice with them, and start seeing some of their applications as well. So let's just start with a brief definition of what an integral is. We call some function f of x an integral or antiderivative of some other function if and only if, when we take the derivative of this capital F, we should get our original lowercase f. So capital F of x is the integral of lowercase f of x if when we take the derivative of capital F, we get lowercase f. So one quick example would be, we have x squared, it would be the antiderivative of 2x. Because when we take the derivative of x squared, we get 2x. Another thing to note, this is just a side note put up in your textbook, but the integral of a rate of change gives net change. So if we have the integral from a to b of some kind of rate, this comes out to be f of b minus f of a, which would give you your net change. So this is kind of the idea behind why when we integrate velocity, we get position. Because velocity is a rate of change of position, so integrating that should give us a net change in position. All right, let's just do a few brief review integrals. So go ahead and try these out on your own. They should be fairly simple right now, but just a couple of brief practice review problems. And on number 2, or on part B, see if you can figure that one out without actually performing any integrals. See if there's a trick you can recognize to solve that one. I'll give you guys just a few minutes to work through those. All right, let's go ahead and work through these. So this first one is fairly straightforward. To be really formal, you can break this up into two separate integrals. The integral of e to the x is just e to the x. And the integral of x squared, we can use our power rule for integrals. And that gives us 1/3 x cubed, again, from 0 to 2. And then when we plug in our limits, we get e squared minus e to the 0th plus 8/3 minus 0. And this gives us minus 1, or e squared plus 5/2. All right. For the second one, we'll do it first just by solving the integral. The integral of sine is negative cosine. And this would give us negative cosine of pi minus negative cosine of negative pi. Now this becomes plus a positive, so we have negative cosine of pi, which is, let's see, negative cosine of pi is -1, so negative 1 gives us positive 1. And here we have plus the cosine of negative pi, which is -1. So 1 plus -1 is 0. An alternative method of solving this is by looking at the sine function and noticing that it is an odd function. And one of our rules about odd functions is that if we integrate an odd function from the same across the y-axis, so it's symmetric across the y-axis, these areas should actually be the same and cancel each other out. So we can immediately say that this is 0. If we wanted to sketch this out, here we would have our sine function from 0 to pi like this. Here we would have our sine function from negative pi to 0 like this. And if I were a better artist, these areas would actually be identical. So the idea is with odd functions, these two areas just cancel each other out and we're left with 0. All right, and for our last one, I'm going to start by rewriting my integral a little bit. First, I'm going to pull out the 1/3. And then I'm going to rewrite my 1 over square root x as x to the -1/2. Now it's in a form where I can use my power rule. That's going to give me 1/3 times 2 over 1 x to the 1/2 from 2 to 7, which is 2/3 square root x from 2 to 7, which evaluates to 2/3 times the square root of 7 minus the square root of 2. And that's as fully as we can simplify it. Any questions? Okay. In that case, let's go ahead and move on to some integrals that are a bit more complicated. So sometimes, or a lot of the times, our integrals aren't going to be this straightforward. Sometimes a problem just looks a lot harder. Well, in cases like these, we want to use something called substitution. And the whole goal of substitution is to rewrite our problem in a way that looks easier. So the way we do that is by making clever substitutions. So for example, let's say I have the integral of the natural log of x divided by x. Well, this integral is a bit complicated, and it might be hard to solve just by looking at it. And we can't really use a power rule because we've got our natural log in here. So what I'm going to do is I'm going to try to make a substitution. I'm going to say some new variable u is equal to the natural log of x. Well, when I make these substitutions, what I need to do is I need to substitute everything with an x out of it. So here, there are three different things that I have that have an x in it. First, there's an x, here's an x, and lastly, I have this dx here. So if I'm trying to make this substitution, I need to substitute out every x as well as my dx. Well, in order to get a dx to substitute out, I just take the derivative of my u equation. So the derivative of u is du. The derivative of natural log of x is 1 over x multiplied by the derivative of x. Well, now, if you look closely, you can actually notice that my integral is the natural log of x times 1 over x dx. The natural log of x is equal to u. 1 over x times dx is equal to du. So I can rewrite my integral in terms of u. Well, now this is a simple integral. I can just use the power rule. And then, because my original equation was given in terms of x, I can substitute u back out. And I am done. Did that make sense? All right. I'll go ahead and do one more example. And then I'll give you guys some practice problems for it. So let's say I have the integral of x times e to the x squared. Well, in this case, or in general, I usually want to make my u my most complicated part of my integral. In this case, I'm going to say I should let u equal to x squared. Again, I need to be able to substitute out my dx. So I take the derivative of my u equation and I get 2x dx. Well, here I can substitute out the x squared. I can try and substitute out my x dx. My coefficients don't quite match though. So what I'm going to do is I'm going to take this du equation and divide it all by 2. And that gets me 1/2 du is equal to x times dx. Well, now rewriting my integral, I have e to the x squared times x dx, which I know is equal to the integral of e to the u squared times 1/2 du. And I can now move my 1/2, just an e to the u, sorry, not an e to the u squared. And I can now move my 1/2 up front since it's a coefficient. And you'll notice in this integral, there are no more x terms, so I've successfully made my substitution, and I can integrate. The integral of e to the u is simple, it is just e to the u. Can't forget my plus c. And again, now I substitute out my u. And I am done. All right. So again, just in general, try to make u roughly the most complicated part. So in this case, the most complicated part was my e to the x squared. So I tried to let my u be my x squared because that was in the most complicated portion. A lot of the times you're going to make the wrong u substitution at first because there are a lot of different possible substitutions to make. And that's really fine. You just have to kind of keep at it until you find the right one. Over time, you'll get a bit better at recognizing maybe which one you should do, but at the same time, it's not always just going to be completely clear which substitution you should do. All right. So time for a few practice problems, I think. Unless anyone has any further questions on theory of use substitution. All right, this is a very powerful integration tool. Now I just have to wait for OneNote to catch up. There we go. All right. Now, I would probably recommend starting with B. B is the simplest of these, although if you know the trick for A is also not that bad. C and D might take a bit more thought, though. Anyway, I'll give you guys a few minutes to work through those. All right, y'all, how's it going? Anyone have any answers?
I actually think we start with the first one.
Try the second one first. That might be easier. Using substitution here. Yeah, but it's you are the type. Yeah, fair. Which ones have you gotten? You get all four of them, or a couple? All four? Nice, nice. All right. Got a few. All right. Say just maybe a couple more minutes, just so anyone who hasn't had a chance to finish up, and then we'll go over them. Maybe 2:30ish. Sid, would you check number 3 for me? That one's not quite right. All right, let's go ahead and go over these. So for part A, the proper approach is to rewrite tangent as sine over cosine. Then, if we make the right substitution, and I'm letting u equal to cosine x, well then we can get du is equal to negative sine x times dx. Now this is important that I use u equal to cosine x rather than u equal to sine x, because I need my du to be in the numerator. If I have a du in the denominator, that's wrong. It'll mess up my whole integral. Basically, your du should always be in the numerator. Well, once I make this substitution, my integral becomes negative du divided by u, which is equal to negative natural log of the absolute value of u. And substituting u out gives me the negative natural log of the cosine of x, and plus c as always. So the integral of tangent of x is not super obvious at first glance, but just remember we need to split it up into its components, sine x over cosine x. The second one, which I think is a bit easier than the others, is a little more straightforward. When we're making our u substitution, we want to make u the inside part of our most complicated portion. That's just a general rule. It's not always the case, but a general rule. So here, our most complicated portion is the x squared plus 2 cubed. So I'm going to make my u the inside of that portion. Well, now my du is equal to 2x dx. So I can go ahead and make my substitution. Here I have the integral of 2 times 2x dx times x squared plus 3, or x squared plus 2 cubed. Now making my substitution, that gets the integral of 2 times u cubed times du. And this part here is replaced by my u, my cube stays, and this part here becomes my du. So I have 2 u cubed du. Well, this integral, I can just go ahead and use my power rule, and I get 2 times 1/4 u to the 4th, which is equal to, if I simplify my 2 and 1/4, that gets me 1/2, and substitute out my u, I get x squared plus 2 to the 4th, and I keep my plus c. Good? All right. This third one, again, I'm actually going to make a u substitution. What you guys are probably familiar with is you're probably familiar with solving an integral like x plus 1 over x by breaking it apart into x over x plus 1 over x. However, in this case, our x plus 1 is in the denominator, so this method won't quite work. What we can do, however, is we can make a really clever substitution, like this. Well, then that says that our du is equal to just dx. So when we look at parts we can substitute out, here I can substitute out my x plus 1 with my u. I can also substitute out my dx right here with my du. But what I'm left with is this problematic x right here. So my goal is to substitute out this x as well. Well, I know that u is equal to x plus 1, which means if I subtract 1 from each side, that u minus 1 is exactly equal to x. Well, now I can substitute out my x. So I'm going to go ahead and make my substitution. X is replaced by u minus 1. X plus 1 is replaced by just u. And dx is replaced with a du. And now I can use that method of splitting up the numerator. And this gets the integral of 1 du minus the integral of 1 over u du, which is u minus the natural log of u plus c. And I just substitute out my u's. Now the interesting thing about this is I can actually combine my 1 and my constant here. So I can even simplify my answer down to an x minus the natural log of x plus 1 plus c. Any questions on this one?
So if you have any number without a variable attached to it, you can just chalk it up to your c.
Yep, you can just kind of, if you have any constant in there, you can combine it with your general constant since it's really not going to change it too much. If we wanted to be really correct, we would label this a different c. So this is c1 because it's 1 greater than this original c. So just to kind of say it's not the same constant, but it's still a general constant. All right. Lastly, we can look at this last integral. In this case, again, we're going to look at the most complicated portion of our integral, the square root 1 plus x squared. And then we're going to make our u be the inside portion of it. Well, what this tells us is that du is equal to 2x times dx. Here, I don't have a coefficient, so I'm actually just going to divide both sides by 2. So 1/2 du is equal to x times dx. Well, if I start making my substitution, I can get the square root of u times x to the 4th times x dx. I can replace my x dx with the 1/2 du.
Why did you just take 2x divided by that?
Sorry?
Why did you leave your x on the one side?
Over here?
Yes.
Because I noticed that I still have an x attached here. So the whole goal is to take all the x terms and replace it with only u terms. So here, the issue is I still have some x's in. I need to think about how to get rid of those x's. I'm going to use a similar trick to what we did last time. Here I notice here's an x squared. So I'm going to try and isolate that x squared. So u minus 1 is equal to x squared. Here I have x squared times x squared. So I can actually substitute that out as well. Since this is x squared, I have x squared squared, or x to the 4th. And then I still have my 1/2 du. Now this is a successful substitution because I've taken all my x terms and replaced them entirely with u terms. So now I just need to kind of distribute and solve. Here I have I can take my 1/2 out front as a coefficient. If I distribute my u minus 1 squared, that's going to be u squared minus 2u plus 1. And all of this is multiplied by u to the 1/2. If I rewrite my square root as a 1/2 exponent. And now I can distribute my u to the 1/2 to everything in the parentheses. And that gives me u to the 5/2 minus 2u to the 3/2 plus u to the 1/2. All of this multiplied by du. All right. Now I can just use my power rule on each individual part of this. That would get me 2/7 u to the 7/2 minus 2 times 5/2 is, 2 times 2/5 gets 4/5 u to the 5/2 plus 2/3 u to the 3/2, and then all of this plus c. Lastly, I'm going to want to distribute my 1/2, and that gets me 1/7 u to the 7/2 minus 2/5 u to the 3/2 plus 1/3 u to the 3/2 over here. That should be 5/2 plus 1/3 u to the 3/2 of c. And my final step would, of course, be substituting my u back out. And that would be my final answer. Any questions with that one? All right. Ooh. So let's go ahead and actually do a brief note on what happens if we have a definite integral instead of an indefinite integral. So I'm just going to go ahead and copy all of this because I want to use it as an illustration down here, but I didn't give myself enough here. Come on. There we go. Okay, so here's our whole integral. We went ahead and made our u substitution, but I'm actually just going to delete all of this part and say, what if instead of having an indefinite integral, we were interested in finding the integral from, say, 0 up to 2? Well, these are bounds on x. They're not necessarily bounds on u. So if I made my u substitution, and I got 2 times u cubed times du, well, these same limits aren't necessarily true for u because I've changed my variable. You can almost think of these as being limits from x equals 0 up to x equals to 2. So if I wrote 0 to 2 here, that would be wrong. So there are a couple of ways we can handle this. We can either write our u substitution integral as an indefinite integral and put the limits back in when we substitute u back out. So for example, we would go through all this, solve, we would get 1/2 u to the 4th plus c. Although in this case, because it's a definite integral, we can neglect our plus c. We would get 1/2 times x squared plus 2, evaluated from 0 to 2. This would be one correct way of doing it. Another correct way of doing it, however, is by rephrasing our x limits in terms of u. Because I know that x is equal to 0 and u is equal to x squared plus 2, I can rewrite my lower limit as u equals to x squared, 0 squared, plus 2. Similarly, my upper limit would be u equals to 2 squared, 4 plus 2. From here, I could just solve my integral. I would get 1/2 u to the 4th from 2 to 6. And then I could simply plug in my limits. And that would get me 1/2 times 6 to the 4th minus 2 to the 4th. And that would actually be my final answer. And that should evaluate to the same as if I plugged in 2 and 0 here. So here 2 squared is 4 plus 2 is 6 minus 1/2 times 2. That seems wrong though. There's something wrong here. Interesting.
One left is 2, all the way to 6 squared.
Right. So this somewhere I went wrong in here. And I'm trying to figure out where it was. Ah, that's what it is. This I forgot to include my to the 4th power here. So that would be from 0 to 2 there. And when we plug this in, here we would get 1/2 times 2 squared plus 2 is 6 to the 4th power minus 1/2 of 2 to the 4th power. And clearly we can see that these are the same. So that's where I went wrong. I just forgot to carry that 4th power there. But they both give us the same answer, 2 different methods, same result. Any questions with that kind of method for changing your limits to represent u? All right, cool. So the method you use is entirely up to you. I'd recommend making it a little more clear which one you're using. You'll notice that I wrote u equals to 6 and u equals to 2 here, just to kind of remind myself I already changed my limits. Okay. Now let's go ahead and move on to the last topic for this one. This is kind of one of the more basic applications of integrals. And this is to find the area between two curves. All right. So if you'll recall, an integral gives the area under a curve. So if I were interested in finding the area between two curves, let's say here I have one curve like this, and I can find its area up till this point, and that area would be something like all of this. And if I had a second curve like this, going up till this same point right here, like this, well, it would also give me a second area right here. Now this is quickly becoming a mess, but if you look very closely, you can see that the area between them is this portion right here. Right about that. Okay, so we're interested in finding this area right here. And if you look really closely, you can notice that if I took my blue area, which has a shape something like this, and my red area, which has a shape something like this, well, I can take my red area right here, and if I slide it right on top, I should have made this fit a bit better, but there we have it. We slide it right on top, we can kind of see that the area we're interested in, this yellow area right here, is exactly the difference between our blue area and our red area. In other words, our blue area, which is the integral of this top function f of x, would be the integral of our top function, or the area of the blue portion, minus the integral of our bottom function, the area of the red portion. And one way you might see this simplified is we can combine the two integrals because we're working on the same limits. So you might see it written like this. All right. So that's kind of the intuition behind what we're going to do to find the area between two curves. This is the main formula we'll be using. So for a quick example, let's say we wanted to find the area between x squared and x. Well, you'll notice here I didn't exactly give any bounds. So our first thing to do would be to find any intersection points, because those are going to give us our bounds. So I'm just going to start by drawing a quick graph. I know that y equals to x looks like this. If I can draw it properly, looks something like that. And y equals to x squared looks something like this. This is not very pretty, but it gets the job done. So I can find my intersection points just by setting my two functions equal to each other. So I'm going to set x equal to x squared. Well, if I divide both sides by x, I can clearly see that 1 would equal x is one solution. And my other solution is just going to be x equals to 0, because clearly 0 equals 0. Why did I put next there? That should be a 1. Okay, so that means that my lower bound is 0, and my upper bound is 1. Now, I know based on my formula that I should be subtracting my top function, or that I said I should take my top function, subtract the bottom function. In this case, my graph tells me that my top function is just x, and my bottom function is x squared. So I take my top function, subtract the bottom function. And this gets me an integral that's pretty basic, and I can just go ahead and solve it. Just using my power rule here. And now I can plug in my limits, and I get 1/2 minus 1/3 minus 0 minus 0, which would get me 1/2 minus 1/3. And just combining fractions gets me 1/6.
Shouldn't the arrow technically go away on the second step?
You are absolutely correct. That should be like that, because I integrated. Thank you for pointing that out. All right, any questions with this? All right. In that case, let's go ahead and do a couple of practice problems for this. All right, and I'll give you guys a few minutes to work through those. How do you determine which is the left graph and the right graph without a calculator? With most of these, so which one's the top and the bottom, I guess? With these curves, they're all fairly straightforward, so you should be able to graph these ones without using a calculator.
I was told just plug in one, whichever one's bigger is your upper.
That's not necessarily always true for
Weird ones that let you change.
weirder ones, but yes, these ones are all fairly straightforward. You should be able to graph them without a calculator. For part A, it's just a couple of pretty simple transformations of your regular quadratic. So f of x is your base quadratic shifted down 2, and g of x is just your base quadratic flipped upside down and then shifted up 2. So if we wanted to sketch that out, which is always helpful, you always kind of want to make a sketch usually. We could start out saying f of x is just our base quadratic shifted down 2. Oh boy. And then we just sketch a base quadratic. Like so. Similarly, g of x, we take our normal quadratic, shift it up 2, and then flip it upside down. Like so. And then you can kind of see that our area between the two curves sits right here. Nice lemon shape. Well, let's see. For part A, 0 doesn't really seem to make much sense because obviously there is an area, right? All of this is it's got some kind of area. So that one probably shouldn't be 0. Let's just go over part A right now. Oh, you used the x values? Ah, yeah, that might do it. All right, I'll give you guys a few more minutes to keep working on it, then we'll go over part A. All right, let's go over these two. So in the first one, our first goal is to find these points of intersection. And to find these points of intersection, I set my two functions equal to each other. And then I can move everything over. I get 2x squared equals to 4. So x is equal to plus or minus the square root of 2. Now that means I can go ahead and set up my integral. My lower bound is negative the square root of 2. My upper bound is just the square root of 2. Now my top function is g of x, and that's going to be 2 minus x squared. My bottom function is x squared minus 2. And this gives me an integral that I can solve. I'm going to go ahead and combine my like terms. I have 4 minus 2x squared, which would get me 4x minus 2/3 x cubed from negative root 2 up to positive root 2. Actually use, this is a few too many square root of 2's for me. I'm going to take note and say both of these functions are even, so their difference is also even. And what that means is because even functions are symmetric across the y-axis, I can actually just take this integral and actually just double it, and instead of having negative root 2 to positive root 2, I can actually just take from 0 up to positive root 2. And what this is doing is it's basically just taking, instead of this whole area, I'm just looking at this portion right here, and then just doubling that area. Because I'm saying that the left-hand side should be equal to the right-hand side. All right. And now all that's left is to just plug in my square root of 2. So I have 2 times 4 root 2 minus 2/3 times root 2 cubed. And then minus all the zeros are going to vanish. So that would get me 8 square root of 2 minus 4/3 root 2 if I multiply out 2 of my root 2's. And I can go ahead and even simplify this if I wanted. So 8 is 24 over 3 minus 4 over 3 is 20/3 times the square root of 2. So that one's pretty fun. All right, now let's take a look at our second one. First off, I'm going to want to draw a graph. Graphs are very handy. And in this case, I actually gave you guys some x values to work with. So I'm going to go ahead and draw those in. Let's say that this is x equals negative 2, and this is x equals to positive 3. I'm also going to go ahead and draw in my g of x function. Right there. We'll call this 1. And also my e to the x function. Now e to the x looks something like this. It's an exponential. I drew it kind of poorly, but you get the general idea. It actually does intersect right here at the point 0, 1. So this problem is a little different from the last one, in that because we're interested in finding the area between two curves, we're looking for this area between the two curves, and we're looking for this area between the curves. So how can we do that? Well, in this case, our top function here is e to the x, and our bottom function is g of x. But over on this left-hand side, our top function now is g of x, and our bottom function is e to the x, which means we actually have to write two separate integrals. So I'm going to break this down into two parts, part A and part B. For part A, I can write my integral. It starts at negative 2, and it goes up to 0, and my top function is g of x, my bottom function is e to the x. And that would get me my area of A. My second area is B, and that starts at 0 and goes up to 3, and my top function in this one is e to the x, my bottom function is 1. And my total area would be a plus b. Well, I can go ahead and solve my first integral. That's going to get me x minus e to the x from -2 to 0, which is negative e to the 0th minus -2 minus e to the -2, which gets me e to the 0th is 1. So here I have 2 minus 1 is 1, minus negative is plus e to the -2. And that would be my area of A. My second integral, I can again just solve. Integral of e to the x is e to the x. Integral of 1 is x. E to the 0th is 1, and 0. That would get me e squared minus 4. Now my total area would be a plus b, which is 1 plus e to the -2 plus e to the e squared minus 4. That gets me e squared plus e to the -2 minus 3 as my total area. All right, any questions on that one?
I'm getting -5 and then -3. I think I don't see why.
Getting a -5 and not a -3.
Also, my e squared is negative.
I'll take a look. -3. And 3 out. So I think you maybe did. Double check the boundary ones because
That's okay. This should be this, but still with that equal -1.
So here we have 0 is 0 and 0.
Oh, nice one.
This one's 1. Minus -2 minus 2 is less than this thing, plus 2 is positive 1. And then the rest is here minus.
Yeah.
You're good. All right. Well, if there are no other questions, that's all for today. Thank you everyone for coming, and have a great week.